welcome to data structures and algorithms in Python. Okay. First, I want to tackle why Python. At first, my programming language here was C++. I thought it was the greatest programming language. And then it became harder and harder for me because, again, I don't have a good foundation in computer science. So I was like, okay, let me try Java then. So I started using Java for my data structures and algorithms. And then there came a time that I was like getting stuck with a lot of coding problems because I'm just creating the data structure, I got stuck. Like errors. And then I really stopped first and I asked online, what's the best way for a non-tech student to quickly learn how to solve problems and learn the concept? And all of them are saying Python. And even like some senior software engineer, they would say, okay, I'm using Java, but whenever I'm doing interviews, I just use Python. So it's very easy. I can solve problems right away. So that's one of the reasons. If you're coming from a struggling to really understand how to code, just go Python for now. Okay. So our agenda for today, we'll do why, Decode, Code Wars. I just want you guys to sign up, create an account. I'll talk more about that. Big O, time complexity, space complexity, linear, bubble sort, binary search, using Python dictionary, linked list, lighting window. So this one is, I want to at least get you the concept in the Big O. Linear search, very, very basic search, just to check where everyone is at. Bubble sort is a sorting algorithm. Binary search is a search algorithm. Python dictionary, because this is very useful always when you're trying to solve coding challenges. Linked list, to create one, design, implement one. That's a data structure. Sliding window is an algorithm. It's more advanced, so I don't know if we'll get to this, but if you get to this, it's really nice. Before I go to why, I'd like everyone to give you just 5 minutes. For those who doesn't have an account yet, go to leetcode.com. Just start creating an account. So while I'm talking, you can go leetcode.com, create an account. So why LeetCode? Because right now LeetCode is the most popular platform in the US. So leetcode.com. Again, why we need to sign up is, again, if you're planning to be a software developer here, this is the best resource that you can get. Because you can find a lot of problems, sort them by topics, and even decide, and even sort them by companies. So it's like, let's say you're targeting Amazon, you can click Amazon and see the list of questions Amazon asks. And again, what's great with this is you can click, you can code there, you can submit your code. There you go. There's a question, there's a code submission. And then there's also a progress status. Like this one. So like this one, solve 721. So for those new people who started trying to solve problems, is I really suggest you to go to easy problems first and just try to keep solving problems. The other thing that I want you guys to sign up very quickly is codewars.com. So LeetCode is kind of challenging because it kind of simulates already the interview style, interview difficulty. Codewars is, again, much more easier. Again, there's a harder problem, but I kind of like that because why? I would see, if you put their client as City University of Seattle, we see people who are actively coding or solving problems. Okay? So, let's see. Next is why. Why data structures and algorithms? So again, we as computer science people, we need to learn how to solve problems, not just do whatever, right? We need to solve problems, and we can only solve problems if we use data structures and algorithms. And again, like what Sam is saying about the brain, so data structure is just a way of organizing, moving around, and storing data. So think of this like storing data in an array, or in Python they call it a list. Store data in a linked list, in a stack, in a queue. You can store data in a dictionary, hash table, hash map. And then next is algorithms are the way to process data. So think of it like when you're cooking. When you're cooking, you need ingredients. You need to put oil first. That's step one. Step two, you put your meat. Step three, you open fire, whatever. So it's just a way to process data. So again, like different sorting algorithms, different search algorithms, they only just have different steps. And again, different time complexity and space complexity. More about that. Then we're gonna go ahead with big O. So what is big O? Big O, big O. Every time they say big O. So big O is basically an algorithm to check according how to their running time or space requirement grows as the input size grows. So it means that when let's say you have an array of students, let's say you guys, and then I want to search for a water bottle. Oh, everyone has a water bottle. I want to search for that paper. I will have to go to 1, 2, 3, then 4. And then now if there's 3 more people here, I start here, it grows. So that's how you think of the big O notation. It's like once the input size grows, meaning the student grows, also the number of steps you have to take grows as well. Okay, input size, again, example, the students, if they become more, for me to find, it becomes larger as well, the number of steps. Okay, I'm trying to just make the concept as easy as possible to understand. Stop me anytime if you don't understand, right? So time complexity, to make it easy again, is just the amount of time it takes to run an algorithm. So if I have to go through every one of you, it's going to be 1, 2, 3, 4. So 4 steps. And we can say that it's the n. It's a common variable we use n times, n number of times. It means I can put 4 times, 4 number of times, or 3 number of times, 2 number of times, depending on the input size. Okay? Space complexity is the amount of working storage an algorithm needs. So let's say you need to store everything in an array, right? So that's a storage. That's going to be O of n. Why O of n? So meaning if I have 10 students, I should have an array or list that can hold 10 students. So that's why it grows as the input size grows as well. Okay? Some would be exponentially, like again, like recursion, because you stack stuff, and more about that. So this is one of your pictures that you should like always have. Again, I would send the links afterwards. So you have the best one and the worst in here. So this is the number of elements. Again, this is the input size. You can say this is the number of students. And this is the operations, meaning number of steps involved. Okay? So we kind of use this. This is a big O. This is the O of n we're talking about a while ago. We're using this different types of big O to compare different sorting or search algorithms or whatever algorithm. So we can say this algorithm is faster than this algorithm. Why? We can say, let's say the first algorithm is O n raised to 2, and the other algorithm is O of n. So the second algorithm is faster in terms of number of steps. Clear? Clear? Again? We'll go deeper into that. So for example, common data structures operations, we would have array. Access time is O of 1. When we say access, when we grab an element. So let's say we have students, 5 students. This is 0, 1, 2, 3, 4. If I say array 1, I get her immediately. If I say array 4, I get him immediately. That's O of 1, constant. You get the constant time. If search, O of n, let's go back again. If I want that paper, I have to go 1, 2, 3, n number of times. Okay? Insertion as well, why? Same. Let's say I want to put a new student here. I would again go through the array, 1, 2, and then I want here, and then I stop. N number of times. Okay? Deletion, the same as well. And again, this is average. This one, this is worst. Big O always deal with worst. Okay, when you say big O is the worst case scenario. Why? Think of it when you're doing business, investing something. You always think about the worst case scenario. You never think about, oh, average or the best case scenario, you win a lot of money. No, you always think about the worst that can happen. So that's how we assess algorithms as well. What's the worst that can happen? Okay, let's move on for now. Sorting algorithms. Now, that's what I told you earlier, is we have different sorting algorithms. And now you can now compare them. Let's say here, just look here, big O is worse, high complexity. And now you would say, oh, this quick sort is worse than cube sort, just by looking at the colors as well. And space complexity, you would see some of them is O of n, as again, it depends on the input size, it grows as well. O of 1, meaning they just use the same storage, they move in place. Okay? Still okay, everybody? Still okay? Go ahead.
So I don't get why like one algorithm you have like best, average, and worst for time complexity. I thought it's like one algorithm that should be like just one best, average, or worst. Like, why you put like three folders?
This one?
Yeah.
Oh, I just got that image from the Google. That's one. And then second is, just to give an example, let's say we go for, let's say we're doing linear search. Linear search is going here, right? Worst case scenario is I see the paper here. That's the worst case scenario. Best case scenario, I talk to him, oh, you have the paper. So it's fast. And then best case scenario, I try to get, oh, the paper's here. So that's the best case scenario. You would have, you can say O of 1 because it's constant. But then again, we want the worst case, which is, it could be there all the time.
So it depends where is the result position, right?
Yes.
So the worst one usually the last one, right?
Yes. And then average case scenario is like, if you run it many times, like I keep searching, you would see the average that it could be in the middle. Right? Now we'll do something more. Again, our purpose first here is expectation, is to understand concept. So we'll drill down to that more. O of n linear time. We talked about this. Okay? Let's say you have only one student in my class who's hiding my bag, who knows about it. Okay? I will ask each of one of you, let's say, do you have my bag? 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 So if no, none, right? But if someone said yes, then I see it. If let's say I look back and you shuffled my bag and I ask again, do you have my bag? Do you have my bag? You said yes, and then I get it. So that's linear search. Okay? Again, worst case scenario, I will have to ask every student. That's O of n. N, input size. Linear time. Linear. Let's go deeper. O of 1, constant time. So this is what I'm saying. It's kind of similar with the search. If I see him, it's constant. That's the best case scenario. Again, you can use O of 1. Is scenario, student who hid my bag, name my bag, I know the name. Okay? Let's say I know Blues. Every time, hey, where's my bag? Blues, where's my bag? Okay, and then I know you always make jokes on me, so hey, Blues, where's my bag? So I know it's always you. So it's facts. It's O of 1. It's constant. I know that it's you all the time. So like, if everyone always, let's say you're just listening to class, someone cracks a joke, you already know, that's Minkyu, that's Gordon. He always makes jokes. So
Suppose in a stack or a queue, if we want to delete the element, for sure it's going to be only the top of the stack or a queue. So is it going to be like O of 1?
So
because we know that it's just going to be the first element we're going to delete, right?
So again, if you're in the stack, you can only get the top one.
Yeah.
So you only access the top one. So that's access O of 1 constant.
Okay.
And let's see if I'm correct. Deletion. Oh.
Okay.
So that one as well with stacking.
So it's already.
So the deletion just for the deleted top one,
Yep.
not the middle one.
So if you design your stack, it's like now we're going to stack. It's fine. So you know when you stack plates, right? That's a stack. Now the question is, do you even get the middle or the bottom? No, you always just get the top, right? Get the top, you give it to another person. So that's basically it. You never go through the middle or the bottom. You always see the top. Again, it's kind of a restriction, but again, there's also good use cases for that. So an example, like why would you use an array over a stack? See, if I have, let's say, I'll give you an example, database. If I have a database that I have a lot of read, meaning a lot of people have to access the data frequently, I would maybe create an array because they also all need to access all the time. If I have a database that I need to insert a lot more than reading, maybe I should think twice of creating maybe a stack or a queue, something like that. Okay? Again, what we love as problem solvers, computer science people, is we want to always know the trade-offs. Okay? There's always something better and something worse. And going back, linear time, next constant, quadratic time. Most of the time, going back as well, I can quickly give you an example. This is like a for loop. For I in range 0 to 1, or again in other Python, one for loop is linear time. Okay? This, not in the for loop. You can use this in like dictionary. Most of the time, it's just O of 1 constant time. O of n quadratic time, usually this is when you have for loops and under that another for loop. Okay? Nested. We call that nested for loops. But before that, let's say the scenario is in the entire class, only one student knows on which student desk my bag is hidden. So now let's add another criteria. Let's say you guys have like a desk inside here that you can hide stuff. Now I would ask, MinQ, do you know which student's desk my bag is located? No. Let's say I ask, do you know which student bag my desk is located? And you would say, oh, it's in Abiwat's desk. So now I have to go to Abiwat and check this desk. So that's why you have like a nested for loop. So I will start questioning each student individually and ask him about all the other students too. If I don't get the answer from the first student, I will move on to the next one. Okay? Worst case scenario, I would have to ask n squared questions, questioning each student about other students as well. So I think that was not a really good example. So I think the way we can make this better is, let's say I ask you, and I have to look to all the other students' desks. If I don't see it, I ask you again, and then I all look to the student desk. I ask you again, and I look to the student desk one by one. So now you see it's n squared. You have two for loops. One for loop, I enter, then I enter again the second for loop to check the desk. I go out of the second for loop, I continue my first for loop, I go here, then I go to the second for loop again to check around. Okay? O of n, logarithmic time. Here, all the students know who has my bag, but will only tell me if I guess the right name. So an example of this is I will divide the class in half and say, is my bag left side or right side of the class? Then I take that group, divide it into ask it again. So let's say my bag is with ZA. Okay? So I can just go ask him, Abiwat, you're the middle. Is my bag left or right? He would say left. And then now I would ask, is my bag yours? Okay, yes. So now it's half the time. Instead of going 1, 2, 3, 4, 5, I can just check the middle, then check again. That's half the time. So let's say we have 5 more people here, and you are the middle. And let's say my bag is with Pepe, right? Where's my bag? You would say the right. And then now Abiwat is the middle. Where's my bag? You say the right. Then now I would see this. Oh, you have my bag. That's still faster than going through 10 students. right? That's half the time. So an example would that be is the binary search. Go ahead.
But does it need to be sorted?
Yes, it needs to be sorted as well.
So log n is like dividing the time by 2 exactly?
Not exactly, but that's a close reference that you divide stuff by 2, something like that.
Or maybe you can think of it like a dictionary book.
Yeah. Mm-hmm.
You're looking for a word, right?
Mm-hmm.
You for example, looking for like linear, the word linear in the dictionary. And then you open the first time you want to open in the middle of the book, right?
Mm-hmm.
Like yeah.
So let's say I want to search for, I have this book. I want to search for City University of Seattle. I open in the middle, and I see letter, what's the middle character?
Oh, I don't know.
M? Let's say I see M. So I know right away I need to flip on the left. And then let's say I open again, I see letter F. Oh, I go left again. And then let's say I go over. I go to letter A, go to the right. So it's left, right, much more easier than going one by one. Okay? Linear search. Again, I would quick overview. That's linear search. We already know about it. Bubble sort. I think this is if you guys are into science, you would see that again. If you put everything together, you mix everything together. Every element or every liquid has different density. And now, if you put them together first here, now you would know that they would kind of sort themselves by density. Lower goes up, higher goes down. So think of it as, again, put them together, and they will bubble up based on their value. Okay? It kind of will sort themselves. And then now you can use this for numbers as well, which we would do coding for that. So later. And here's the number. Too many images, so later. It's the mid and high. It's binary search. Stacks and queue. Again, you can only access the top in the stack, and the stack is first in, first out. Oh no, first in. Good. First in. So first in, second in, third in, last out. Okay. Queue. You can think of it as like you're lining up to Starbucks. The first in, first out. If you're the one who lined up first, you get to get the order. So for Python dictionary, as we all know, dictionaries, or sometimes in other languages we have hash map, hash table. It's key value pairing, right? So now in Python dictionary, this is the syntax. You put a variable name, and in the variable name you assign an object with this notation. It's called the curly braces, and in the curly braces, you now have to put a key. And then to separate key from value, you need to have a column. Okay? And now this is one item in the dictionary. This is another item in the dictionary. This is their key. This is their value. Question? Again, we're still in the overview. Reakless is basically you have a bunch of nodes. We call this nodes. This is a node, this is a node, this is a node, this is a node. And each node has two things. One is has the data, which is this node has A as their data, B as their data, C as their data. The another thing is they have a pointer. Again, if you remember your C++, I forgot about it because it's done. So if you know about your C++, again, you can assign any names for this. We can say next is a pointer to this node. So now when I do node.next, I will get this one. Okay? So another thing that we put in linked list is, aside from the node, the linked list itself, so these are nodes, and this is a linked list. A linked list would have a head pointer. A head pointer would just help you know where you currently at. Okay? And again, want you to know that at the end of the linked list, it always points to null. So if you traverse, meaning you go through it, so when you go through it, 1, 2, 3, 4, and you see null, means you're at the end of the linked list. Okay? Again, this is different than array or list, just because in array or list, okay, I access this, fine, change it. No, in linked list, I want to change sheet, I need to go here, and then change this one. Okay? And then, but then again, it's better than array and list in another sense. In array and list, if I want to insert, let's say here, I have to go to A, B, then insert. For linked list, I can just say insert, and it will always insert here. Okay? And again, for linked list, we can have 2 pointers for the linked list. One is the head, and actually this one should be like tail, and they would point to each other. What this helps is now you can quickly go to something. Let's say it's in, let's say you have the same linked list. You want to go to 4, you have to go through everything. But if you have this structure, a double linked list, if you have something here tail, you can access 4 right away, or half the time if it's in the middle. Okay? So I hope we're also able to reach this again. It's a sliding window algorithm. So usually you would tackle this if the problem says, give me the maximum sum of a contiguous subarray. So I'll dissect that for you. So let's say you have an array, and a subarray is basically, let's say you have min, q, ia, lose, root, and you indeed list, right? When I say subarray, I would say min, q, and ia is my subarray. Okay, that's a subarray. And if I say contiguous, it just says continuous. So if I say min, q, ia, you are a contiguous subarray. If I say lose and then lin as my subarray, they're not a continuous or contiguous subarray. They have to be connected. Okay? And that's done for the overview. Let's go to some coding. It also has like index and values. So think of it just a mini list or mini array. So if this is hello, O is index 0, 1, 2, 3, 4, index 0. H is index 0. Okay? So we just need to do a, I don't know if it's the correct term, like a nested access. So the way we do that is, at first, this one prints everything, right? And then because, again, what we said is the string is also like this, that you can access the index, so just put 0. Still okay?
Yeah. We can treat string.
So before we move on to like the binary search stuff, I want to go through the slicing first, then dictionary, then let's go to the algorithm. Slicing is really good. Is, for example, I want to print everything. I can do something like print word, and slicing is like this. You put square brackets and you put 3 parameters. Optional, again optional. So if I remove this, I should get the list of words again. Then, no, actually, is it this one? So I'm getting only that, so no. So again, let's say slicing, reverse. Oh, because I'm just doing word. That's why. So if I want to return the same list, that. If I don't want to, let's say, please print me the words list without the first element, you can just do 1 here. 1. Okay. This is what we call slicing. I don't know if other languages has this, but Python has this. So you can slice list. You can also slice strings. So again, what string? So for example, I want to access hello, and then first let's print just hello. Oh no. Why do I keep getting that one? I think it's because I'm reusing the variable.
No, words. Words?
Words 0. Yeah.
Yeah.
There you go. So this one just prints the word hello, and then if I just want the ELLO, just put 1. So now you kind of know right away is when I put 1, this one is the start. I want to start at index 1, which is world. And this one, I want to start at index 1 of the first word, which is E. And then print everything.
Would you put into the before print just the words without the slicing, and then how about the outcome?
So the first one you would see would.
Just you print the words. Yeah.
Yep.
Almost that.
So again, this is printing all the words in the list, which is this one. When you use slicing with this way, putting nothing, it's basically just the same.
Yeah.
Okay. Now, if you want to use the power of the slicing, you can use the start. Another way you can use it is you can also use the. Let's try to remove this now. You can also do this. No. I want to print 2 values. 2 values. So now what this says is, because I don't have anything here in the first parameter, it assumes I start at index 0, and I want to do 2 values or elements, which is hello world. And in this case, I want to start at the first index, which is world, but I want to print until the second value, which is world. So I guess this position is wrong, sorry.
Would you show another example after last column? You can put in
Yep.
another example.
Okay, next is moving that first.
First and 2 and column, and can you use something? Let's say start with a 2, okay?
2.
2, and then you are 3. Or 2. But you show the column 2, column, something like 1 column, 2 column, and do you need something else after column?
It's optional.
Optional, but minus 1, plus 1.
So default is 1, and like let me explain because right now we're here. So what this one is, I'll take the whole list, and I start at the index 0. I stop at the end, but wait, I have 3. So what happens is, I first print hello, then 1, 2, 3, and print that, and 1 more 2, 3. That's why it's only hello Seattle. Remember, slicing is one of the things that after the session, just learn more about it because it's a great toolkit to do some solve problems. And this one is again, I want to start at the 1 doesn't make sense. Let's do 2. So this one, let's see again.
No, it's over there. City, Seattle.
No, I mean this one. So original is this one. So what happens now is I want to start at index 0, which is city, print that, and I want to count 2, 1, 2, and print that. now we know that, we can now know how to reverse. Like that. So again, to explain this, I want to start at 0 and at the last, whatever. But because we have this negative thing, it will go through the end and reverse it. Go ahead.
Actually, for skipping one element,
Mhm.
method what you did using the for loop, I just didn't give the last parameter -1,
Mhm.
and it just showed me as error because what I thought was like -1 will come from the last
Oh, again, what you're using, range? Is it range?
Range, yeah.
Okay. What's your first parameter?
So my first parameter is length of word -1,
Okay.
which is like it will start from the last
Yes.
parameter, and -1 is it'll end in the first parameter, right?
It would not. It would end at the first.
Yeah,
parameter.
first parameter. So I thought I'll just leave it just like that, and I just printed and it showed me as an error.
Because why? Because again, as the default, your third parameter, it assumes that you do +1.
Oh.
So you start at the index 9, right? +1. So more. You want to do -1 to go to the
So
index.
for sure, if you're using the first two parameters, for sure then you have to use the parameter.
You need to change the step.
Oh, okay. Thank you.
Okay. So we'll connect this now. Oh, question.
Oh, no, our student, they need a break.
Okay, go ahead.
No, not now, yeah, after we finish.
Yeah, after the fourth question, let's take a break.
Okay, sure. Fourth question, we already done this. So before we go to a break, let's introduce dictionary. So let's say I have hello. Hello.
The first thing I want to try so it's 7. So you can treat this one is the index go up or down. So 5 minus 1 is open. So because for the negative number, so we can just treat that like index plus or index. So I don't think here for this. So we will minus 1. I don't have the thing in here. So that's why the first number is set.
Okay, so before we take a break, now I changed up the words to include duplicates. Okay? So now we have duplicates. My first challenge before we take a break is create a dictionary. This is already how you create a dictionary. Use a variable name and assign a curly bracket that will initialize that dictionary. And now if you want to add in the dictionary is you use this syntax, use the variable name, square bracket, your key, and assign the value. So if I print dictionary, that one. So I'll change it to a better word. So this is the clue, and let's do this challenge number 5. So Challenge 5 is iterate through the array, add the word as a key in the dictionary, and let's keep it that simple first.
If we miss dictionary initialization, what happens?
Let's see. Okay. So with the challenge number 5, I'm expecting first question, can I do multiple keys? No, yep, okay. Expecting unique words in the dictionary. To iterate over the dictionary is yep. Okay. Okay, let's do this. So first things first, don't forget to okay. Make sure your word list is now this one. You have an extra Seattle and you have an extra two of those. Do that first. Let's do words 2 instead, so that we have a new one. Words 2. Words 2. So that when I give you guys the code back, you can still reference to this properly. Yep. Create a list called words 2 and add 2 of those. 1 Seattle. And then again, I want you to create a dictionary. This is already the answer. This is an example of how you add a key value pairing in a dictionary. This is the key. This is the value. And the next step is this is how you iterate over the dictionary. So for in the keyword. This one is just a variable name. You can do anything like values, key, whatever. And this is the dictionary, the object. And you can just do print items to print it out. So the very easy challenge for now is I want you to iterate through the list, word 2, words 2. Go ahead.
Do you have to use item or items? Which one is the better?
I think items.
Yeah, singular.
Excuse me, I have a question.
Right.
In the 47 line, shouldn't we use the function print or we just put the item?
So that's just an example. So you can do print or not.
So it's just
In your case, you would want to print it. But then again, you want to first do a for loop, either to the words to, and then again you need to add the word into the dictionary. So when you print now, so when you do this, when print item, I should see no duplicates. Okay.
Can I use this way to read? Set equals.
Ooh, I don't know set. Well,
Yeah, after you set the so the result is unique.
Mhm.
I have a list, so I should look on the list and see the key.
Yeah, so I add another thing. So add word as key and one as the value for the key. Let's do that for now.
Oh, one.
Yeah, let's do that for now.
So usually it's one.
You can do anything, but I would still extend that after the and change that. The next thing I would ask is count the number of duplicates. I mean count the frequency of each word. So what was your next question again? Yeah. Correct. Then you can just, after you put everything in the dictionary, you can now iterate in the dictionary and print the item. Are you able to do it? Or so first create the words too. You can just copy the hello words you see and all that stuff. So it doesn't have to be the correct spelling, but I want to have like duplicate words in your name too. So you can have bye, John. Yeah, that should be fine. Then now is that's an example. So I'll give another clue for everyone too. So I'll add an extra tip. So when you iterate through the list of the words, let's see. So I'll just add another tip for you guys. So you're iterating through the list, right? You're going through hello world, axis, gal, right. So now my extra tip would be when every time you loop, you access the value of the list in word 2, then use that value as the key in the dictionary. So this clue means is first loop I get hello. I use hello as this one. So basically I don't want a hard code, meaning just put hello here. You need to put an example is words 0, words I, or words 1, 2, 3, 4. So now you would put hello here with not using the hard code, with accessing the list. Okay, quick example, I'm gonna delete it, is something like words 2 and then I. Every time you loop. Okay? First tip, iterate through the list. In every loop, I want you to access that value. You access the value, or again the word. When you access that value or word, now use that as the key to the dictionary, and then now you assign 1 as the value to that key value parent.
So why you chose again the orange one? Just it doesn't matter?
Because I want you guys to take a break first.
Okay. We're giving the homework, no break. Everybody have a break.
Yeah, actually, if you guys want to grab, go stand up.
So the next step is duplicate, right? So I use hello.
words 2. And then access the value of the list in word 2, which is words 2 I. You would get to access that. And what I'm saying is use that value as the key in the dictionary, meaning you should do this and do this. And then now I say this is already adding the word as the key to the dictionary and put 1 as the value. You only want that for now. And the way we can print those dictionary is we can do the first one. We can first print the dictionary. We can also print the what's that? So yep. So printing the dictionary, you would get the all of the contents, key value pairing. And then when we iterate, one is key values in WordDict items. You would get to access the key and the value, and we can print the key and the value, which is this one. Okay. And then next is we can also use this is the dot items. Okay. If we only want keys, use the dot keys, and we can just print the keys. And if you want the values, just print dot values. Okay. Now we want to just quickly extend this is number 6. Count the frequency of each word. Then print the dictionary. So when we say frequency, if I see 2 hello, my dictionary should have, let's say I have 2 hello or 3 hello, this should be hello then 3. Okay. A clue for that is you can use the same one. Comment that out. So first tip is using if and else. An if and else statement looks like this. Let's say 1 equals 1, turn true, else turn false. That's an example. And then tip number 3 is number 2 is using the not keyword. I'll go ahead and write that. If blah 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 not in WordDict, then else. So tip number 3 would be if the word is not in the dictionary, add that to the dictionary. Then tip number 4 is the else. Else, if the word is in the dictionary, add +1 to the value. Okay? Try that and let me know if you're stuck just because of syntax. I'll go ahead and help you out. I'll go around. This one is, no, it's all of one. This is the dictionary. So I always check the dictionary, it's all of one.
So,
If it's there, I get it. If it's not, okay.
so it's not indexed because
It's not. This one is, this is all open because you iterate through the list. Okay, but this one, whenever you check the dictionary, it's all open.
all.
That's why, again, in coding challenge, most of the time, if you want to keep track of something, always think of dictionary right away. Dictionary or hash map, whatever, hash table. Because if you put everything in the array or list, it's going to eat a lot of performance or space. So. Okay, extra tip for this one is if the word is not in the dictionary, add that word to the dictionary. The way you do that is basically you access the word in words 2 and use that as a key. A sorting algorithm. It's called bubble sort. So to first have a bubble sort, definitely you would have one-to-one unsorted array. And if you have an unsorted array, you also need a for loop and another for loop, which is a nested for loop, and a variable to switch number. For Python, you don't need this. So to visualize first, the bigger number bubbles up. So if this is 34, this is 10, the arrangement would be 10 and 34. The bigger number goes to the left, or bubbles up. So given an unsorted array, you have 65, 34, 25, 12, and 9. You start with this one. First loop, you have, I'll show you first the for loop. So essentially you would have something like this. Nums 64, 34, 64, 34, 25, 12, 22, 11, 19. Okay? And you would have something like for I in range, nums, for j in range, nums, start at j is 1 plus I, j plus 1, j So first things first, you would have two for loops, I and j, let's say. And let's go back first to visualize this. For now, don't take much of the, I guess just look. So we have 2 pointers. One is this one is this one. The first thing we do is we compare. We start with loop 0, compare this one. Is 64 bigger than 34? If yes, let's swap. Okay? Swap. Next thing is, now 64 is here, it will compare them. Is 64 greater than 25? Yes, swap. So it will keep doing that, swap, swap, until it reaches here. Let's see here again. Is 64 greater than 11? Yes, swap. And now we evaluate, is 64 greater than 90? No. So now
The gray indicates that this is now sorted. This last element is sorted. I don't need to check that again. Okay? So now we keep doing that. We start again at the very beginning with 2 pointers. We check. Is 34 greater than 25? Yes. Move that. Swap them. Check again. 34 greater than 12. Swap them. Greater than 22. Swap them. 11. Swap them. Is 34 greater than 64? No. So now this is sorted. Okay? So now you see it's bubbling up. It's pushing the bigger number to the last, to the end. Third loop. Same goes with that. Until you have everything sorted. To implement that, it's very, very easy. You just need to traverse all through the array elements for this again. And then the last I elements are already in place, meaning sorted. And then again, this is the other loop. That's why we have 2, is because we want to have 2 pointers. So we start at 0, basically. And n is the range, which is, let's say you have 10 elements. Length, right? 10 elements minus I minus 1. Okay? Traverse the array from 0 to n I minus 1. Swap the element if element is greater than the next element. So I'll first go here, explain this one, then this one. With this one is j, and one is j plus 1 in the first loop. This is 0, this is 1. So now you check. Check that here. This is that one. If that is correct, let's switch the places. And in Python, again, in other language, you usually need to create a temporary variable. But in Python, you can just use 2 variables, put a comma, and then equals, just switch them. And now that switches the value. So if it's, let's say, for example, this is 10, this is 12. Now this becomes 12, 10. That's how you swap in Python. Okay, now to, let's see. Now to discuss why we do the n minus 1, n minus I minus 1. So the first time we go here, this is I equals 0. That's the, like the outer loop, right? Once we're done with that, wait, sorry. This is the, I think I should create 2 pages to quickly switch over. So j starts at 0 as well. I starts at 0, which is this one. That's why we got this. Okay? Now, when I is equals to 1, what happens is n, which is again the total length. Let's count 1, 2, 3, 4, 5, 6, 7. 7 minus I, which is 1, which is, sorry, it should be here, which is 7 minus I equals 1, 6. Okay, never mind. Again, I'll repeat myself, sorry. So what happens here is it goes to the J for loop, and whenever I finish one J for loop, which is this one, now you see that's why I grade this out. It means that because I minus 1, I would never go back to this again. Because I is equals to 1. Now my length for the J loop is only until here. Okay? When my I is 2, again, my for loop for the j variable is the length, which is 7. Wait, no, 1, 2, 3, 4, 5, 6, 7. The length is 7, but because it's array or list, so it's minus 1, and then minus I, which is 2. So we don't need to touch this because it's already sorted. Okay?
I is equals to 3.
Again, the J loop would have n minus I, so minus 3, and then minus 1, which is this one. If you don't do the minus 1, you would have a 1 of error. Because again, index starts at 0. Okay? Again, quickly explain that. So, for j in range, start at 0, which we always start. See, we always start at the beginning. Whichever I we are, we start at the beginning. So, n minus I. If you do 7 minus I, it's 3, right? Which is 1, 2, no, n minus 4, which is 1, 2, 3, 4. We still have one more, which is minus 1. Okay, again. So j is equals to 0 until n minus I minus 1. We have 7 elements, but the index is 0, 1, 2, 3, 4, 5, 6. Okay? 7 elements, but we have index only until 6, right? So that's why we have the minus 1. So now we have 6. But because this is already sorted, that's why we minus 4. Because you don't want to go through this again. Okay?
So that is bubble sort. So you can go ahead and just put this here and you guys try it out. Oops. Return. Okay, not yet. Return. Swap. Because of this one. It's not sorting. Why is that? It's wrong. Should not be that one. Oh, okay.
Yeah.
It works?
Yeah.
I feel like there's a bug.
What is the P example? I mean, in the terminal.
Terminal?
Yeah. Is it like P? Is it Python?
Oh, yep. That's Python 3. Can someone find the bug if they can?
You turn meant to be outside of the ballroom.
Yeah.
Clark, can you move over here?
Up.
Yes, go up.
I'll try to remove spaces. And then put this. So we call this sorted nums. Okay, I'll move on. Next, we'll have the binary search. This is a very common search algorithm, and the way we implement this is basically. Let me try to write this for our children. So let's say we first need to have a sorted array. So let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. So you have elements is 10 for value, and your index ends at 9. Okay. So again, with binary search, the way we do this all the time is we first go to the middle, go here, and we also require a target. Let's say I want to find the number. I want to find the number 7. So what happens now is because this is sorted, I first check the middle. First, where is the middle? So what you need is length of nums divided by 2. That's your middle. So when you start, you check the middle. 1, 2, 3, 4. So middle, because you have the floor division. So if it's 10 divided by 2, it's going to be 5. 0, 1, 2, 3, 4, 5.
now you would ask, is the middle, which is 6, is 6 greater than 7? If no, it's no, right? So what we would say is, okay, I know everything on 6 left, the left of 6 is smaller, everything on the right side is greater, so I'll say, okay, I will start looking here on this part. So now you see that you already have the time right away because you don't need to search here. You just limit yourself here. Now, one of your questions would be, when we still did not do that, the start is at 0 index, the end as was the index 9. When we did this, what happens now is the start becomes 6, the end is now 9. Okay? And then when we go here, we divide again the difference, which is divided by 2 is 1. So from here, you can see here, let's say this is the new middle. We ask again, is 8 greater than 7? Now what's different is, if this was false, we look at the right. Now, if this is true, we look at the left, which is only this one now. And then now, my new middle is this one. Okay? So, thing is with binary search, even though let's say it's already beside 8, you still need to do that same process until the value that you're looking for is the same as the mid. Okay? Another example?
Should we use recursive for this?
I don't think you need to.
Actually, in this one, you have to use recursive, right? Because we are just common changing the start and the end, right?
You keep changing your range.
Yeah, but you can just change the range with the left and right. So,
You don't have to use recursive.
Oh, the green is not good.
You can use it like normal loop. Normal loop?
Yeah, and then
Update. But you don't know how many times you should. So you mean use while?
Yeah.
Use while and just judge the range, right? The length of the range until what, and then just break.
Go talk. I'll just quickly grab a better pen, because I'll make that more clearer with the left and right.
The primary. Are you still doing the sorting? This is okay.
guys can see better here, right? So I'll show the code as well while we're explaining this one. Oops. Okay, so it's been a long time, so let's verify this code as well. So let's have the numbers again. Let's take these sorted numbers. 11, 22, 12, 22, 25, 34, 64, 90. Okay. Now, during this time, we want to create something that would, I keep calling it pointer, but again, to have a variable that would track the position in the list. So we want to start with left at index 0, which is this one, right? We want to start at index left minus again these nums. Then nums minus 1 to get this one. Okay. Now we'll have a while loop while left is less than right. So when we start this one, 0 is less than 0 less than 6? Yes, so we go inside the while loop. And we have another thing that we need to keep track, the mid. Is mid would be left, which is 0, plus right, minus left, which is 6 minus 0, divide this by 2. This one becomes 3. So this is 3. And that's why when we start, this is 0, 1, 2, 3, 4, 5, 6. In binary search, you have a sorted array, always start at the middle. This becomes the middle. See? Okay. Next is if mid equals to target. And now let's say we want to search for 64. We want to search for target is, or 25, let's use 25. 25. We want to look for B. No, that's bad. Let's go 64. Let's go 64. We want to search for this one. Okay. And now is mid, which is this one, is it equal to the target? I think this is searching the index. Target index, target. Okay. So I need to, this one should be nums. So now I can compare is 25 equal to 64? Wrong. So I don't go here. So let me just write this down as well. So we skip this first, and then we go to else. Else left equals mid plus 1. So because we didn't go here, we go here. The left variable, which is our kind of pointer, moves. So it becomes mid, which is 3 plus 1. So our next left would be, so I'll have a table here. Left, right, mid value. So it's easier for us to keep track. And then let's create something like this. In the first loop, you have 0, you have 6, you have 3, and the value for that is 25. And the target that we want is 64. The next is, in the next loop, we go update the left, which is now 4. Right is still 6. So now you see the scope becomes here. Okay? So that now we do this, we go here. If it's left still less than right, yes. 4 is less than 6. And now we enter this, we update the mid. We need to update the mid. Mid is now, this one will be 4 plus right is 6 minus 4, and then divided by 2, which is 2 divided by 2 is 1, and 1 plus 4 is 5. So mid is now 5. So that's how you compute for the middle. Okay? The mid value for that is now 64. And then now we enter here is the value for that, which is nums mid, which is nums 5, is 64 equal to 64. Yes. Actually, we don't need to do right. Oh, so yes, that one is wrong. So now it should go to just return. Return the index, which is mid. Okay, let's do this one more time because we want to fix the code. So I think it might have some problems here. If our target is, say, 12, let's do this again, left, right, mid value, starts with 0, 6, 3, 25. And let's just try to do this. This is the turn. Nums. Okay. Actually, just sorry. We want to get the position. Okay. Now let's say we want to search on the left side. Okay. So first we go here again. Initialize. Left is less than right. True. We go in here. Mid. It becomes 3. We start with this one. Try to remove this one first. So we start it over. And now we go here, and then if it's equals to target, meaning nope, because right now we have the mid as 25. Is that equal to 12? Nope. So it goes here, which we need to add something more. Do else left equals mid plus 1. We should have an else if. Right equals, so how do we move that? Mid, let's see if this is correct. Mid minus 1. Would that be correct? Let's see. So else if right becomes mid minus 1, which is your left still is 0. Mid minus 1 is 3. So 3 minus 1 is 2. Let's see if that's correct. Yes, it's correct. Now we can look here. This becomes the mid. And the value for that is, mid is 1. Index 1. The value is 12. So far so good? Good, okay. And then now, we can loop again. Is left less than right? Left is 0, right is 2. Yes. We go inside this loop. Now mid is left 0 plus 2 minus 0 divided by 2, which is 1 plus 0 is 1. So now your left is your mid. Sorry. Your mid is. Sorry. Wait. Oh, sorry. Mid is 1. We go here, value. Oh, sorry. But this already ends because we saw 12, right? So mid is 1, mid value is 12, target is 12. Now this satisfies. Okay? Because now 12 is equal to 12. Just let's say we extend that. Let's say we want to get the value for 22. What happens now is if we want value 22, we're already here. And then we go to LF. So this one is also need to be changed. If nums mid, if nums mid is less than target. Okay. Now we continue this. We start with again with okay, let's reset. Let's reset quickly. So we start at 0, 6, middle is 3 and 25 every time because that's the middle. Second loop now is mid. We go here, which is now updates to mid minus 1, 2, 0. Value of that is 22. Mid is 1. It goes back again. It's less than right. Yes. Goes here. Mid is now 1. Still 1. Not be 1. Oh, this is 12. Mid is now going here. 0 plus 2 minus 0 divided by 0 is 1. So mid is still 1. Huh. Nine is 2. Oh, because this one, we should go here. Sorry. So yes, so because when we are here, nums mid is 12. Is it less than the target? No. So it goes here. We update the left, mid plus 1, which is 1. And now this is still 2. It's become 1. 1. This is 1. No, 2. 1 plus 1 is 2. Now we get it. And mid value is now equals to target. Okay? We're going to go ahead and fix this. And do we go for lunch, Sam? Fix this as nums mid. This is nums mid. Nums mid is less than target. Let's update the right. This is turn nums mid. See if that works. Yes, it works. Let's try some more. 64, 90. So I'm returning the index. So for 25, I should get the index 3. And for 64, I should get the index 5 and then the index 6. So, and then something is wrong. This one. Yep. 356. Yep. So great food. Let's have lunch. And when we continue, we'll talk about the recursion and dynamic programming. Let's now go to the topic of recursion. When we say recursion basically means that in this scenario is it uses the same function. So let's say I have a function factorial. I also use the same function. I keep calling it until I reach a base case. So a perfect example to use this is factorial. For factorial, let's say you have a 5 factorial. To get the value, you need to multiply 5 times 4 times 3 times 2 times 1, and then now you get 120, right? So first, for recursion, you have to know that recursion uses what we call a stack. So again, what is a stack? Let's say you have plates, right? For when you have 4 plates in the stack, you can only use this one, and you have to remove that to get this one. So going back to this example, this is what you call a call stack, still a stack. Why do we say call stack? Because whenever you invoke a function, you basically call a function. So that's why you call it a call stack. So let's now try this out. So when I put the number 5, it goes in here, right? Is 5 equals to 1?
No. So it goes to here. So let's keep track of n. So it says else the n. Let's keep track of the n. Let's have starts with 5, and the other one is factorial n minus 1. N minus 1. Factorial. So what happens here is because this doesn't have a value yet, it goes inside the call stack. You would see here factorial, which is n minus 1, which is 4. No, I think it starts with 5. Because it doesn't resolve, right? Again, the only way it will really resolve is it comes to here. So we call this, and then n is now 4. And then when it's 4, it needs to call it again. So this is, let me fix this. This is, sorry. This is 5 times factorial of n, so 5 minus 1. Now you would have 4 times factorial 4 minus 1, 3 times factorial 3 minus 1, 2 times factorial 2 minus 1. Now, when we go here, 2 minus 1, so it becomes 3, 2, and now when it becomes 1, we achieve this base case. Okay? Now 1 is equals to 1. Now we can start using 1, which is 1 times 2. Again, this is 1, because we returned 1. So I'll expand this to visualize it. So it's 2 times factorial 2 minus 1, which is, this is 1, right? And this is 1 as well. So 2 times 1 becomes 3 times factorial 3 minus 1. Now because we finished this, we now get 2 here. This is the value 2. And then now we have 4 times 3 times 2, 6. So the reason why I'm still showing this is because right now this one resolves and it's giving the value of 6. And now we have 5 times 24, which comes from this one. Get an answer. One thing. And what happened there is the first time n was 5, it can't resolve because it needs to call the function again. So if it can't resolve, we put it inside the call stack. Right? Just put it in the stack first, we'll deal with it later. Okay? And then we go inside again, becomes 4. 4 is not equal to 1. We do this, but again, because it calls again, we put that in the call stack again. It becomes 3. 3 is not equal to 1. Goes here, push that in the call stack. Goes with 2 as well. And then when 1 is equals to 1, and now we have a value 1, this is the time we can get the value for this one, and this one, this one, this one, this one. Okay, so recursion itself is very beautiful, very elegant. It looks very simple. For a first timer, it might be confusing. You have to keep reading on it again. But once you get it, it's good. But because again, with recursive function, you take up a lot of space. Because what if you have a factorial of 100? So that's going to be a big problem. You would have a lot of this in your memory.
Okay, it's gonna be there in the memory until it reaches 1. So that's why we have to introduce a different type of way of programming, and we call it dynamic programming. So in dynamic programming, but basically what we need to do is not do a recursion and make it like a iterative approach. So let's call this factorial iterative, and let's get n. And inside of that function, I would say sum is equal to 1 for now. And I would create a stack. Again, you can use list as a stack. That's fine. And then we put the first number inside the stack. Then now we have the while loop. I'll write this down first and let me explain one by one. So that one, then for num in stack, sum times equals num, else stack dot append -1, return sum. So for you guys, I'm going to visualize that in the board. Let's use this. Another one. Let's use this. So we would still arrive at the same answer, but now we're using list as a stack, like this. Let's keep track of the variables first. We have sum. Sum is 1, right? Next is we have a list stack. Empty. And then now, what we said right away is append. So that's just a method for list that we want to put. So right now, again, as I said, we want to keep track of the variables. Sum is 1, stack is now starting with this one, and now it's has 1. Okay. While sum is equals to 1, which is yes, it's 1. What happens now is it says n equals stack -1. Okay? Sorry, correction. So, because the function has n, and this is stack, that append n, let's use 5, just a correction, this is 5 right away. Is that correct? 5? Yes. So when sum equals to 1, we go inside the while loop. And now n equals to stack -1. It means the last element. The last element we only have in that stack is 5. So n started with 5, and it's still 5. Okay? Now we go to the if statement. If stack -1 is equals to 1, which is not. So we don't do that first, we do the else. The else stack dot append and -1. So now what happens is we push another one to the stack. Now let's keep track of our stack here because it's gonna be long. So we started with 5, and now once we enter the if and else, the else, we append again, meaning we add, so that's 4. Okay? And then, because we're still in the while loop, sum is sam is equals to 1, So still go to the while loop. And now we reassign the value of n, which is now, what is stack negative 1? This is stack, so you get 4. So now your n is 4. Okay? Is stack negative 1, which is 4, is it equal to 1? No. We'll not do that. So what we do now is stack that append n minus 1. So your new stack would be like this. Okay? You go inside the while loop, is SAM equals to 1? Yes, still. Because we never update this again. Okay? So we still go to the else statement. It goes 5, 4, 3, 2. It goes in the while loop again. It's going to be 5, 4, 3, 2, 1. It goes in the while loop. Now it goes to the if statement. If stack negative 1, which is right now it's 1, is it equals to 1? Yes. What we do is sum times no. Actually, yes. There's a for loop here. Num is stack. So a while ago, guys, we already learned about this type of for loop. It just means that if I have 5, 4, 3, 2, 1, I would access 5, then loop, then 4, then loop, then 3, then loop, then 2, then loop, then 1. So now what happens for this, let's go down to the for loop. So in your first for loop, what you would have is 1 times, which is num, this one, 5. Then now 5 times 4, 20 times 3, 60 times 2, 120 times 1. So you now arrive at the same answer. So that is by using the iterative approach, they call it dynamic programming, instead of using recursion. Okay? Is this clear? I'll show another example for Fibonacci. That one has a cooler iterative approach. I think I can just grab quickly the code. Let's see. Let's start with this one first. So again, we start with recursion. So now, Fibonacci sequence, if for those who doesn't know, it looks like this. So something like this. Nope, not that one. Okay, so let's try to do a, say, Fibonacci calculator so we can quickly check if we have the same one. Say Fibonacci of 10. Let's just do 5. No, this is not Fibonacci calculator. Why can't I? There you go. 6. Too much. So the seventh Fibonacci would be 30. Okay, let's try that. I'll explain this again using the this one. I think it needs a bigger one. Let me remove the self as well so it's not confusing. Okay. So let's say we have again 5. So what we do is if n equals to 0, let's keep track of our variables. N start at 5. This one returns 0, so we don't go inside here. We go here instead. If equals 1, which is not as well. Turn 1. Else is turn fib n minus 1 plus fib n minus 2. Okay? So now we're doing 2 function calls in one function. So now we would have so we start here is now you would have fib, which is you start with 5. 5 minus 1 plus fib 5 minus 2. And then now basically it calls twice, right? So you would have 2 of them. Let's say first fib, then second fib. After the first one, becomes 4. 1 is 3. Call it again, because you don't satisfy this, you don't satisfy, so you go here again. So you have fib 4 minus 1 plus fib 3 minus 2. Okay? So now it becomes 3 and 1. For the other one, it still doesn't satisfy, so we would have fib 3 minus 1 plus, now you have 1, and because it's 1, you return 1, so now it's 1. Okay? So far so good? Okay, so now you have 2, and now you have 0. So now this is fib 2 minus 1 plus 0. And then we go call the function again. This is fib. Well, this is 1 already, 1. This becomes 1 because this becomes 1. And for the other one, becomes 0 minus 2 negative 1, which is weird now. So I think it stops at here. So let's try. So for this one, we have 1 plus 0, which is 1. Then 1 plus 1 equals 2. 2 plus 2 plus solves, we have 3. No, again. Let's try to execute that first. Don't want to make mistakes with that one. do a 6. 8. So, because we're using 5 a while ago, so let's confirm the 5, if we can get the 5. And let's print, keep printing. Okay. Oh, by the way, can you see it? Can you see this part? Okay. Okay. So going back. So when we reach this one, we return 1. Now we get 1. And now this is now we have 1, 1, 1, 1. I think this becomes 1, 1, 3. Okay, let's try to repeat this again, because I got confused a bit. If anyone remembers the Fibonacci, just go ahead and correct me. Let's do this again. Fib n minus 1, which is 4 minus 1, plus fib 5 minus 1, 5 minus 2, fib 4 minus 1, plus fib 3 minus 2, fib 3 minus 1, plus 1. So this resolve, this doesn't resolve yet. So this is plus 0. Fib, which is 1. So this becomes 1. And now I got that. And then 1 plus 1, 2. I think this is it's way harder to write it. Let me quickly check that one.
No, you need like you need to separate count
You need to separate the
because
separate stack.
no, I mean because 5 fib 5 equal fib 4 plus fib 3, right? So fib 4 equal fib 3 plus fib 2, and in this part fib 3 equal
Mhm.
fib 2 plus fib 1. So you need to like separate
So I should.
just like a note and
So what you're saying is, oh yeah,
so it's kind of like a pyramid.
separate, right? Know what you're saying?
No.
Right.
Just like so like this is 3, 5, right?
Mhm.
So the syntax is like
So continue. I'll check if my code is correct. Yeah, so code is correct. I'm just doing n equals equals. N equals 2 and 1. I think this should be this one. Let's try this one. 20, it's 9. Yep. Oh yeah, right.
1 and 0, it will stop. So that's how I explain and count.
So basically what he is explaining, which I totally missed, is again, whenever we do the catch, when we do one function call, it goes calling two function calls again. That's why it expands, 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 expands.
So the n minus 1 and n minus 2 happens in the same loop.
Yes, in the same call.
Oh, yes.
So yeah, so if you want to resolve this, now you would have n equals to this one is 0.
No, but 1 is 1, 0 is 0.
1, 1, 1, 1, 2, 3, 4. Still looking for 1. So I think it's, let me just check. So maybe it's 1, 2, 3. No. I'm getting it. 1 plus 0.
I didn't separate this one.
Yep.
So I missed it.
Oh, there. So 1, 2, 3, 4, 5. Right. One, 2, 3, 4, 5. There we go. So this is also a perfect example why it's a good practice to present and whiteboard, because even I know Fibonacci already, but I totally miss how to write it or diagram it. Forgot about it. So here, basically what we get here is, again, whenever we pass a number in our Fibonacci, we call two Fibonacci functions. Okay, every time it goes back again, it calls 2 again. So think of it like the monster Hydra. You cut one head, it goes 2 head. You cut 2 head, it becomes 4 head. So think of it like Hydra. And then now, once you reach Fibonacci 1, that's the time it becomes a value 1, and then you start adding them up. And again, that's why I want to show you the iterative approach again, which is beautiful, because now we can see the use of stack, or again, list as a stack. Oops. That should also do the same thing. Okay, let's use the other board again. And this time around, before we are just adding to the stack, and now we're trying to also pop the stack. So we start with that empty stack. Let's keep track of our stack here. It starts as an empty stack. And we go to the second line, we append n, which is 5. So now stack is 5. And now sum is 0. Let's keep track of sum here. And what else do we need to keep track of? Fine. So while length stack is greater than 0, which is the length of the stack is now 1. Is it greater than 0? Yes, we go inside. Now, what we want to do is assign a new number to n. So n started with 5. Okay? And then we want to pop. When we say pop, let's get the last element and remove that from the array, which is this one. So when you pop that, when you pop that, it becomes still 5. Okay? And then I think this becomes none for now. And then is n equals to 5? Nope. Is n equals to 1? No. Else, you append to the stack again twice. So now you would have n minus 1, which is 4, and n minus 2, which is 3. Okay? Now you still go to the while loop. Is the length of stack greater than 0? This is 2. Is it greater than 0? Yes. Go inside the while loop. We pop the stack, get the last element, pop it. Now n is equal to 3. Right? Yep. And then it doesn't go to the if, does not go to elif, goes to the stack that append. So now we would have 4, 2, 1. Okay? Goes to the while loop again. Same thing, it's still greater than. Now you pop this, remove this, becomes 4 and 2. And now n becomes 1. Now because n is 1, we add it to the sum. So now sum is 1. Okay? Now we go inside the while loop again. And when we go inside the while loop, we pop, we remove 2, n becomes 2, sum, and then n becomes 2. Now we append that again.
1 and 0.
Yep. 1 and 0. Now, what happens here is you go inside the while loop, you pop this, n becomes 0. And if n becomes 0, you plus 0, which is against the 1. So now this becomes 4 and 1. Next is you have 4, and then you pop the 1, so n becomes 1. And now you add to the sum, 2 becomes 2. Okay? Do you still have the an element in the stack? Yes, so you go into the while loop. Now this one becomes 3 and 2. Okay? You pop this out, this 2 becomes 3. Let's continue n here. Now you would have 2. And then you go, when you have 2, you go to the while loop again.
1 0.
Now it becomes append. 1 and 0. This one adds to 0 and adds to 1. Comes like this. Comes like this. Okay? Next, this will become 2 and 1. And then you all know what happens with here. 2 and 1.
1 up and plus 1.
Then we pop the end. This is 1. Becomes 2. This one becomes 3, 4. And this becomes
1 0.
1, 0.
4 1.
Now we add 0,
0 0.
which is 4. We remove the 1. Add the sum. Reach the same number. And stop. So essentially, a Fibonacci of 5 is 5. A Fibonacci of 6 is 8, and so forth and so forth. It's just so happened 5 is 5 as well. So again, this is the beauty of using the list. It grows, it shrinks, it grows, it shrinks. You can do the same thing as well as doing the recursion. But again, take note, if a while ago, in the recursion, you're just doing one function called 1, 2, 3, 4, 5. In the Fibonacci recursion call, it kind of grows. Like for every 1 you have 2. For every 2 you have now 4. And now it's so much more memory. And this one is just a while loop. This one is just a while loop.
So this one, the complexity is
Better.
It's better than the recursive, right?
Yep. Again, sad to say, recursive is not really a good time complexity and storage, stuff like that. Let's just fix this. Okay, so when we try to use that, fib 5, yep. So to check if it's the same as the fib 9, should be the same. Nope, it's not. Anyways. But at least, again, you get the concept. That should be fine for now. Okay. Again, this is what you call dynamic programming. Different paradigm to solve problems. And I think we can now move on to, let's try linked list. Linked list is something like a train linked list. So remember I showed you this image that you have nodes and heads. Okay. So if you haven't done Python object-oriented programming before, we're gonna enter to that space. So first things first, what I said is in the linked list we do have nodes, right? Nodes, 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 and nodes. So why not create a node first? Class node. Okay? And then when we initialize, we want to have data or value, whatever, self.next. And then when we initialize, we should also grab the data. Wait. Let's see. What's that again? Niklas. Okay. So definitely, again, here's how you create a class for Python. So sorry for that. And then inside the class, definitely you will want a constructor. A constructor is basically when you create an object from a class, you initialize it. So the way you create a constructor is using the underscore init. And then you must call the self. And let's say value, set it to none. Or data, let's put data. Then when we create a node, an empty node, we should have self.data equals data and self.next equals none. Okay. To explain this, we have a class node, we have a constructor, so this one, underscore init. This one is a requirement because self is pointing to the class, so you can access whatever members of the class is, which is the node. This is an optional default. So if I create a node and I didn't pass any number or data, it becomes none. But if I pass, let's say 1, the 1 becomes the node's data. Okay? So what it means is if I create a node, new node equals node, say print new node, I would get the object's address. But if I access the data of that node, I get none. If I do next, I should get none as well. Okay? Okay, do that. Now, if we want to create another node, a newer node, let's say, we add data, let's say 100, print newer node, address points to none for now. and then now the data should have 100. So go ahead.
Why you don't need to create the value, like the variable?
Because we want to do this in such a way that we can create a linked list, an empty linked list with an empty node.
I mean the data, right?
Why is it
like,
not?
Because we need to create the variable first, and then assign the variable.
Oh,
But why Python don't need?
so this one is creating the variable.
So
Yeah, so I can actually create this as val. So that's how you create variables inside of a class. You need a self, so it's like node.val.
So if I don't want to use constructor, I want to use that getSet function. So how do I do that? Like, do I need to put the value both in the front and use getSet function to assign value or get value?
Get set, you would still do some get set, but without the constructor, I think you, let's see. I think you still need to do some get set. I don't know if I understand the question correctly. Again, you said if I don't have a constructor, and then, or you,
I only have so I mean, because in your way is you to use the constructor to create a value, right? So if I don't use constructor, how can I create the
for the
value?
node.
Yeah.
For the node.
Yeah, for the node.
Well, we can try that, but I don't. So I think you can create a variable, but you can never access it as part of the class. I think. She's in Vietnam. Kim?
Kim's not here.
Kim? She's in Vietnam, vacationing for several weeks now.
Sorry, I keep seeing your emails. I thought she's gonna be here.
Oh, okay.
Or Tuesday.
Yep. So I'll try to research more on that, but I think the answer is you need to put it in the constructor so that it's linked to the class. Or maybe I just didn't understand the question as well. So moving on. Moving on. So now we have this. We can create a very simple linked list without extra structure or whatever. So we can create first node. This node, let's say, has a value 20. And we can say first node, second node has the value of 40. Right? So right now, if I do connect them, again, the next is like the pointer. First node dot next equals second node. If I print first node dot next dot data, I should be able to access the second node, which is no attribute data. Wait, first node dot next, get that, and then why doesn't it have data? Next, different memory address, correct? First node dot next. Oh shit, that's mine. There you go. So I want this concept very clear. And for those who are like getting lost, just keep trying to understand, listen carefully. And before, when I started, what I do is whatever I don't understand, I just write it down. Like I Google it afterwards or ask the person afterwards, so that you don't lose any information at all. Okay? So, so this one, first node, when we created that, we would have something like first node. When you want to check the value, it's going to be first node. Data, and it would generate the 40. So what it means is, let's say I have this node, and sorry I forgot to explain, a node is basically one of the data structure. It's just an object that you can store data. Okay, so let's say this is your node. You created node 20, so now it has value 20. Okay? Before this one, before the second node, first node is still like this. First node dot next value is none. It means if you invoke first node dot next, it points to nothing. Okay? Now we create a second node, which is 40. So now when you access the second node dot data, sorry, this is 20. And what it means is that you have something like this, 40, and then you do this. Next, second node dot next, none. It's still none. So this still points to none. So this is just to show you that first node and second node, they begin with being separate. They're not really connected at all. But because we did this, basically what we said is first node dot next, and assign what address or value is the first second node. So what basically happens is this one says now it points to the second node, and this one still points to one. Now they are connected because of this one. First node dot next. Okay? That's why now I was able to do this when I say first node dot next, which is this one, dot data, which is this one. So again, when I say first node dot next is this one, and dot data is the value. And that's why I was able to print 40. Still okay? Still okay? We can stop here for like a little bit while so you just understand. What part do you have any confusion? So again, what if you print first node? What's the question? You can. Is that your question? If you can, or you can? You can. Oh, okay. So because personal dot next equals second line. Did you save it? Oh, this one. Because we changed it a while ago just to show what it should be. Great. Okay, we can continue with this one, and let's now create like a linked list. Again, I want this to be cleared up. You have a class name node, which if you invoke it with node and this one, it basically creates an object of that class. And now the def init basically is a constructor. Basically means that if I don't pass anything, my data would be none. If I pass anything, the data would be that value. So when it goes inside the constructor, you have the data member of the node class, which is self.data. And what this one says is whatever I pass, which is the 20 and 40, please use that 20 and 40 or 40, assign it to that node's data member variable. Okay? And self.next just points to, just have the value of none. Now, it's going to be more complicated. Because we want to create the linked list in a proper way. So we want to create a class linked list. And again, we want to initialize that, the constructor. Okay. So we already went through having a node and having two nodes and just connecting them. And now we want to make it in the proper way. So we now create a class called linked list, in short. And whenever I invoke the linked list, then the parenthesis basically says that create a linked list object or data structure, and then initialize with a pointer head. What is this head? Again, in the pictures that I explained a while ago, this is just pointing to the node. So basically what I mean, if let's say I want this to be head, I'll just say this is head. Something like that. Okay? I'll explain more. I'm back. So in this case, I can create an object of linked list and assign it to the variable called myLinkedList. When I print linked list, basically I just get the object's address. If I print the dot head, which is also the address of the node, again, the first one, when you print the linked list, it's the object of the linked list, address of the linked list object, okay? The next one is the head, which points to the node. And again, as you can see, the node is an object as well. So now the node object at this address. So you get the address of the node. Or basically the object. Okay? Now because that is also a node, so you now access to the property of the node, which is the dot data and the dot next, which is for now it's none and none. So in this case, we already create an empty linked list. Okay? Now, what we want to do for the empty linked list is, what if we want to add stuff there? Okay? So if we want to add stuff is, move this for now. We create now another method called, let's say, add head, meaning we want to add at the head. And then what we want to do is use self, and then when we have that, you now have if self dot head dot data is equal to none. Meaning, remember when I created an empty linked class, it's just created something like this. This is my linked list object. And in my linked list object, I have a token. Okay? We started with that, and this one only says that with my self, because we initialize this as our head as well. Say linked list dot head. Linked list dot head is this one. And again, this one you can access the head dot data, which is none. Right now, head dot next is also none. Okay, so we start with the empty linked list, having the head as the pointer, and we want to check if head is one dot data, which is this one. Again, it's this one. Is none, which is yes. Okay, and that's a yes. We can insert at that point. Let's insert self dot head equals node data. Node data. So let's try to sample that. So let's say my linked list dot at the head. Let's say I want to add the number 5. So to check that, now I could just print linked list, no, my linked list dot head dot data should have 5. There you go. So with this line of statement, it says, okay, that satisfies the condition. So when I get a new node, it's called 5. What I want to happen is, please make this as the head. Yep. Okay, here. So think of it, the first node was just like a dummy node. Now, what if we have something there already, like that one? So basically, let's create a new node. Dot new node equals to node data, and new node dot next head self dot head new node. So if we had another one, say 8, should be 8. Okay, and if we have head dot next dot data, it should be 5, 8 and 5. So to explain that, so we currently have this. So let's just write that again. 5, and we inserted 8, right? Now we have 8. We created a new node data, which has the data number 8, and new node dot next is now the self head. So we move this from this head. We remove that, put this here. No, sorry. That was the next slide. Before that. Yeah, let's start off with this one. New node equals node data. We created the 8. New node dot next, which is this one. Again, the dot next is this one, right? Now it connects this one. Because before that, head is still this one. So it says, connect this node to self dot
next line, what happens is we're moving the pointer head, not the pointer next. So now this is still like this. It's connected. So points are not. This moves. Now this is doing it. Now we are able to create an empty linked list. We're able to add nodes at the linked list. So what else? So go ahead.
Pushback. Else.
Pushback.
Maybe what else?
What else? We can first try to implement a print function, and then let's also do the delete, insert, and other stuff. So to print it, you can just say print self, and then in that print, you want to check if self.head is not equal to none, meaning we have a node. That's what it means. Then let's assign parent node to head, self.head. Okay, and then because we want to print out like a string, so we can create something like string, and then string current node that data. Okay, while current node dot next not equal to none, current node equals current node dot next, string equals to that there plus string is bigger, string current node data, then at the end after the while loop we want to show this one as well, it points to null, which is the current node string current node dot next, and then return or just return print string. So let's see if that one works first. Let's remove this for now. My linked list dot print. There you go. 8, 5, none. So again, I'll explain this because this is also a useful way to traverse in linked list. Basically what we're doing is we're traversing and moving through the nodes in the linked list. So now we're starting with just the two. Start with this one. 8, which is the head. Points to, which is the next, this is the data. 5, this is the data. Next is none. Okay? When you first enter the print function, it says self.head. Is it equal to none? Well, head is equal to no. So we enter the if statement. The first thing we do is we create a variable called current node. And we did assign what? The self.head. So I would get this one, which is this one, that node. Okay? Next is I want to create a string. This is a string. And basically I want to, if that, because again, that's why I put the str, it means if it's a integer, I'll make it a string so I can like print it as a string. So now I would say, have this. I would have this as a. So now we'll enter the while loop. The first current node you want to move, you want to make the condition first. Current node next not equal to none. And when we try to evaluate
definition. Why are we doing that? Because when we're here, is next equal to none? Nope. So we move. Is next equal to none? Yes, we stop. So that's the purpose of that. So now you have the current node equals current node dot next. So what this means is that because we already stored this in a string, we don't need 8 anymore. So we need to change this, which happens here. We need now to change this to 5. Again, that's why I'm putting the square, because you're not really grabbing 8, you're grabbing the whole node. And this again, when you say current node dot next, it means this whole node, make it as the current node. Okay? Now we have that, this one. We now have the string again. Now it would look like this for the first. We would have 8 arrow. And then we access again the current node data, which is now this one, 5. And then because 5, when we check, we go to the while loop, is it none? Yes. Now we go out of the while loop. And now we create another string. And it should now look like this, which is 8, 5, dash, none. Because again, this current node dot next is already none. Clear? Tell me if you want more example, more clarification, because I'll move on. I mean, I'm still in Niklas and show more methods. So far, so good. Okay.
There's no one.
Up. Okay. Let me know if you want me to repeat it again. Repeat and repeat, totally fine until you get it. Yeah.
So if you create an empty node,
Yep.
and you want to judge it is none or not, is it will none or
None. For
still none?
Python,
Yeah,
it's
for
none.
Python.
None.
So even you can get the address of that node, still none.
Address of the node.
Because there in the initial constructor, you initialize the head.
Yeah, we
node.
can put this
But
as
it is
none.
empty, right? And still, you still can print the head node, just the address.
I was doing that because. Yep, you can fix it like that. So to explain what just happened is, the other one is, you can call it less efficient or whatever. Is when we create an empty like this, we need to create this one. But when we add another one, disregard this again, and just create this one and this one. Basically, this improvement. This basically says that. Oops. Basically says that when I create a linked list, it's not. You might just do this, but it's still the same. But I think that's way better.
So we don't need to create here, right?
Hmm?
No.
Not yet. Don't do this at the end. Single linked list first. Yeah. Hello. So what if we want to get something, like get the index of the value. Let's.
Hold it.
Yes and no.
It's on your way.
So let's first add some values again.
So we are going to get the index of the value.
Yeah, we want to get the index. So let's say. So this would be, let's say, 0, 1, 2, 3, something like that. Okay. Let's now create another function called get. In that get, you again need the self, and you pass the. Let's say we want to get the. You want to get the value or the index? What do you want to get? Index or value?
I think it's if you put the index, you want to get that value.
Yeah.
If you put the value, maybe you want to get the index.
Yeah. What do you want?
Value.
Okay, you want to get the value.
Yeah.
Okay. So with the index, so first is let's see is if index equals to 0, then just return the head.
Head
stuff
no.
That head
Yeah.
not, and then we want to return the data. So to explain this first, so if the user says, hey, I want to get the value at index 0. Oops. So I can just try to print that as well. So I should get 2. Yep. 2. So this half-finished function basically does it. When the user inputs 0, is 0 equals to 0? Yes. If that's the case, I don't need to look around. I can just access the head, which is this one. Remember, we always update the head, right? Whenever we add another one, we move the head pointer until here. So just to quickly show that, 8, 5. So when we have 10, 8, 5, this becomes the head. We move that. And then when we have 2, 10, 8, 5, we move that again, this becomes the head. So what we're saying is, if we want the value at index 0, just return the head and the data. We shouldn't not return only the head because it will just show you the object. Okay, now else if. So what if the index is greater than the, let's create a length function, a length variable. Current, no, self.length. But we don't have that. So what we can quickly do that is, why not, when we initialize, we'll just create a variable called length, initialize to 0, empty linked list, right? 0 length. And whenever we add something,
Length plus 1.
we just do length plus 1. I add this to the top because it doesn't matter whether it's a if or else, it's still gonna add. So I just put it on the top. So just to check this first is when let's print the length to confirm that. Self.length. Four. I have 4 elements. Okay. So now going back. Okay, going back. Else if the index that the user is asking is greater than the self.length. An example would be my length is only 4 and someone asked for 6, index of 6, it does not exist. So in that case, I just return -1 just to denote that it's an invalid index. Else, meaning it's valid, everything's valid, what we do is while current node,
I think it's bigger or equal.
bigger or equal to,
Because index usually is less than that.
okay, let's see. Let's see. So if we get 4, yep, should be, yeah, it's correct. I think it's correct, right?
Like,
Go ahead.
so in this case, your index, the max is 3, right? Index is
Oh,
3,
yeah.
depth
Oh,
is
yeah,
4,
yeah.
right?
Yeah, because
So if I
length
put
index,
4,
length and index.
yeah.
Wait. 0, 1, 2, 3, and 4. So my index couldn't be 4.
More than 4. No,
More than 4.
More than 3.
More than.
Not equal 3. More than.
Okay, again. So my length is 4. I can't have a 4.
Yeah.
I can't have a 4. Yes. Correct. Then now, if it's valid, we do a current node dot next, but we don't have that yet, so we put that on here. Let's say. Just to make it look cleaner, let's put it on the top. So let's create a current node again and grab the head. Okay. Now else while current node dot next, if it's not equal to none, I can keep moving.
Bring and move, I think. Right.
And we want to check what index we are currently at.
So we have to keep a count.
Yeah. So I can just say count, and then count plus 1 whenever I move. We already add plus 1 because we already skipped the index 0. And then if index is equal to count, meaning it match, so we just return the value of the current node dot data or next or data.
Data. Current.
If not, let's reassign the current node with the next node. Let's see if that works. So let's see, grid 3, 0, 1. Oh, we're off. So it's gonna be turned by
No, you
dot.
didn't move to the next.
Yep.
Oh.
Yeah, that works, right?
Yeah.
So let's quickly have this explained. If so we're done with index 0, that's fine. Else if it's fine, it's more than. And now if it's valid. So why did I change the number? What was that number again? It's 8 whatever.
285.
210,
210.
85. Okay. So 210, 85. This is data, this is node, 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 this is pointer next, pointer next, pointer next, pointer next. Okay. Because let's say we want to get the index 3.
value at index 3, which is 2, 3. So we want this. So the way we do this is while current node dot next is not equal to none, we keep track of count. Starts with 0. Now it becomes 1. If index is equal to count, 1 is not equal to 3. So we skip that. We go move current node equals current node dot next. So at first, the current node was nothing, but because we assign this is the head, that's because we assign self dot head, current node now holds this. And then when we reach there, we say the current node dot next is now the current node. So now this becomes the current node. It's just moving around. Current node is now this one. Okay? We go to the while loop. Current node dot next, is it not equal to none? Yes, there's still a node, so we go inside the while loop, increase the count. Is count equal to 3? No. Now we move again to current node. Current node dot next, which is this one, the arrow, which is this one. That now becomes the new current node. Okay, this is the new current node. Goes up. Current node dot next equals to none. Nope, there's a node here, so it's not none. Go inside, increase my count to 3. Now is 3 equals to 3? Yes, it is. Now what we want is, hey, can we return this one, current node dot next? So it grabs this node. Can we return that node? The node's data. So we grab this and return this one. Hence we get 5. Here? There?
So that's why Linux is hard to get, so hard to assess the value. So
Assess the value.
Yeah, it's kind of linear search.
Yeah. So we can quickly talk about just to connect stuff with the algorithms. So I mean the Decode is if you have a list or array, if this is a list, 3, 5, and you have this linked list. For arrays, whenever you access, it's O of 1. When you mean access, hey, I want to access nums, index 2, which is 8. I get that right away. I can do whatever, access, right? If you do access for linked list, if I want to say, hey, I want to grab the 8, it starts at here. It doesn't know where the 8 is. So it will check this, then okay, now I know the 8. So that's why it's all of that. Think of it again, it's like a linear search. I check each one. For array, for list or array, I can just say, oh, it's here. Oh, it's there. Okay? In terms of the other way around is insertion. When you insert, now array has a problem. It becomes O of n. So let's say I want to insert at index 0, index 2. I would go 1, 2, 3, which is index 2, and insert here. So you need to go each and then insert. So that takes time. While linked list, the insert time is O of 1. Because it doesn't care when you say insert, it just adds a new one. Always adds a new one. Doesn't care.
But if you say that we have to insert the element after, let's say, 8, it means that it has to travel to.
Yeah, now you have to O of n.
Okay.
But most of the time, you just add it. You have to do it.
I have a different
Right.
opinion.
Oh yeah.
I think for the array, so you want to insert one element, right? So like for example, I want to insert a middle. So it's easy to okay, I just no problem.
You want this one?
So
moving the elements.
For moving, because this one need to move this one need to move this one, like that. So it's moving. So this part is we cost a lot of time. But for the link, funding is hard. But after funding it, I just cut this one and link each other. That's it. So usually the time complexity is depend on the head or the back. So usually the array, if I want to insert a value, if I want to insert a head, it costs a lot of time.
Yeah.
Because they need to move all of the elements. But if just the back is very fast, just O F1. O1. So yeah, nice.
Yeah,
That's
that's a
all.
good
Yeah.
argument. So again, as we can see in this chart, we go back again with access, very fast, search, insert, deletion, very slow because then again, you go to that element quickly, but you have to move the elements, which make it slower, right? And then now in linked list, again, we're doing the same thing linked list for now. Access and search, because you have to keep checking the nodes. Insert and deletion, most of the time you use the head or just the tail. For now, we're just using the head. Okay, so what else do we want? Oh, let's try to. What do you want to do first? Insert or delete? Insert or delete? Insert? Okay, let's do this. So for the insert, let's see, I think insert and index, yes. So let's create a method again. Add index self, then the value or data, and then once we have that, so want to know where we want to insert. Okay, so basically create a function called add an index, and it should include two parameters: where we want to insert and the data that we want to insert. Okay, so because this would still insert regardless, so we can increase the length right away when we call the function. Okay, so let's create a new node and basically create this one and then get the data from that. And then now the next is, let's always do this, the current node equals to self.head, so we can move through the linked list or traverse. And then let's also have a count like before. And now we have the count. We can also put the if index equals to 0. And what's nice with this is we can just have a new node dot next, attach it to the current node. And after we attach it, we move the pointer. Self head equals new node. Okay. Quickly explain that first. Is and we are I want to keep repeating so it gets through our heads. So add an index. If the user says, okay, I'll add index 0 and my data, let's say, is 10. So what happens now is my new node should have a node that has the value of 10 that still points to none. Every new node points to none. This is the next. Next is the data is 0. Okay. Now we always do this. The current node equals self.head. Just to move around again. Don't mind the count for now. If index is equal to 0, which is this one, we now enter new node.next. So we need this one. we want to connect it with current node, which is the self.head. So let's say when we have this, 8 and 5, and this is the head, what happens now is it goes to the head, which is this one. So that now becomes connected. This is still the head. Because we said, new node.next, please connect me to the current node, which is the current node is the head, self.head, which is this one. Now that's done, don't ever forget to move the pointer. You just move something like this. Move the head here. That is just what happened. So now the self.head is this one, the new node. Okay? Now, if not equal to 0, elif index, let's use that same thing, greater than equal to self.length. Should we just, I guess we can do just greater than. Insert at the end. Because we can insert at more than the length, right?
Yeah.
Yeah. So return -1. Else, then don't need to do. Oh, so now let's do. Yeah. Wait, I might need to change this later. Okay. Let's see. It did not account for greater than. Okay. Else, if we increase the count to 1, and then while count is less than index, keep looping. Current node equals current node dot next, meaning let's move around the nodes, traverse in the linked list. And now we have to increase the count again because we moved. And now we have the current node equals current node dot next. Oops. And new node dot next is current node. Let's see first if that works. Let's remove this. My Niklas dot insert at index index 1, the value of 500. Does that work? Index 500.
You didn't print.
This one. Nope. So because count plus 1, count index, let's see, dot next, zoom out. Current node equals self.head, and if index, nope, so I go here, so count increase, then count.
Oh,
This one?
I think it's current node next equal new node. New node next equal.
Current node.
Wait. Let me think.
Current node dot next, and then I move. Or should it be? Then I increase. If it now goes out, current node. Current node dot next. New node dot next is to the current node. Current node.
Oh, you need a temp node to store the current node next.
Let's see. Dummy node. Current
Node next.
node dot next.
Then
Current node dot next.
and then current node next equal new node.
see. Count node at that equals new node.
Yeah. And new node next equal equal dummy node. Yeah.
Let's see. There you go.
And the third one I think is
Does
yeah, is
okay, okay, so we just swap and yeah, check the points. Let's check first if what if we done something like 1, 2, 3, 4, 5, which is 4. If we do 5, okay, good. What if we did 8? Should not work. Okay, cool, works. Okay, 3, okay. No way. What X, right? Okay. So, let's start with just inserting the one number. So now, okay. We start with having 2, 10, 8, 5, none. This is the node. This is the data. This is next. This is the node. This is data. This is next. Node, data, next. Node, data, next. Okay. So our function, which is add index, we said we want to insert at index 1, which is should be here. And then we want to insert the value 500 or data 500. Now we skip the if, we skip the else if, we go to the else right away. Our count starts as 0, sorry. And by that time it entered the else, it becomes 1. Okay? Now it's count less than index. Is 1 less than index? Which is no. Bad example. Let's change that. So I want to enter the while loop, so let's have a better example. It's 2. There you go. Again, let's change this to 2. So now we enter the while loop. Go here, want to go here. So is 1 less than 2? Yes. And then current node, dot next. Again, before that, what we did was this is the head, and we initialize with having the current node, having the self dot head. So this is now also the current node. That one. And now it says current node dot next, which is 10. The 10 node is we want to move the current node. So this one started off as the 2, and now it's the node with the 10 data. And now we increase the count again. Okay? So is 2 less than index, which is not. So we exit the while loop, we now go here. We create what we call a dummy node, just to swap values or nodes. So basically what we want is, because this is now the current node, right? Current node dot next is this one. So what we're saying is, let's hold that 8, node with the value of 8, with the data of 8, and then next is the current node dot next. What we want to do with that is, we now assign the new node, and the new node was this one. So this was like this, right? So So current node dot next is now 500. What this means is this is still the current node, remember? This is the current node. Now it will point to 500. That's what happened. Current node dot next, it now points to 500. Go ahead.
I think you don't need to worry.
Dummy node?
Yeah.
Okay.
You just have the new node next, point to the current node next.
Okay, let's go to that and see if that works. So new node dot next
Next, point to current node next.
equals
Current node next.
current node next.
Yeah.
Yeah, I think that will
No, the order should change.
current node dot next.
The order should change, and then you can stop use.
Why we need that is because it will override.
No, if you change the order, like if you because this is the same thing, right?
Mhm.
If you write this first, it will over.
Yeah, override.
But if you put this one
On the top?
first, yeah, on the
Yeah.
top, then this one this one will
Current node dot next would be this one. Right.
Yeah.
Right.
Yeah.
Good catch. So we can further improve this with this one. Don't need the dummy node.
Yeah.
Still work fine. So to fix that, when we go out of the loop, new node dot next is equal to current node dot next, which is current node dot next. Current node dot next is 8.
Yeah.
This one. Again, current node, this one, which is this one, dot next is this one. That's why we got this one. Okay? Now, what we want to do is current node. I guess the previous one was just easier to grasp.
Yeah.
Because you can connect and connect again. So, I think it's better I explain that first and then improve it. So, they get to see the two perspectives. Okay? Again, once you're just doing beginning stuff, is you kind of wanna, if you wanna see the whole picture, it's okay to have a longer code, and then just try to refactor them. Because if you go shortcut right away as well, sometimes you get confused. So let's go back to here first, and let's go to the improvement. Okay. Dummy node. Again, this is the 16, 11, and 11, and okay. And whenever you kind of hear the problem, like find, let's say the maximum sum of a contiguous subarray. So those are kind of like the keywords. So if you have a string, they may say substring. This could also mean continuous. Okay. What it means is that this is a subarray. This is a subarray. This is a subarray. This is a subarray. So basically, everything inside is a subarray. And now, to satisfy the contiguous subarray, it just means that they have to be connected. So this is a contiguous subarray. This is a contiguous subarray. This is a contiguous subarray. This is not a contiguous subarray. This is not a contiguous subarray. That's it. So when we are asked to find the maximum sum for a contiguous subarray, the problem now is the way you're going to look at is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9,
specify all the elements, and it would take you a lot of run time, which you don't want. So again, just to limit this code so that this is easier, we're gonna do the fixed size, meaning the user would input what size. So if I say I want a window with a size of 3, meaning I